All right. Well, if you're watching this not live, I'm on here early and I'm trying to figure out some things. And this is all new to us. There's a big delay from my screen. So I'm going to try to view this on my iPad as well and see if I could bypass that delay. So we'll see. My iPad has 4% battery, so that's a problem. Let's see how we do. So please fast forward like 8 minutes if you're watching the recorded version of this. YouTube. Oh, hi, Tom. Okay, I'm trying to figure out how I can do this where I can see it. Oh, and now I hear my echo. Anyways, there's a big delay if you remember last time. And so I'm hoping that, but I know that you guys don't see the delay. It's just on my screen. So I'm trying to see if I can see the comments on my iPad so that I could like not have to worry about that delay because that was so annoying. But I don't know how to do that. We're early. Sorry, Tom. You're on top of this. I miss you, Tom. Are you wearing your shirt? Your Old Navy one? Oh, hi, Emily. Yeah, and I remember watching Mr. Johns and he asked someone to comment and then he was like, "Come on, let's go." And I was like, "They commented." It was so annoying. But I don't know on my iPad if I can see the comments. I had the brilliant idea that I would watch it on another thing. I'm glad you're still in PJs. This forces me to actually get ready, having these YouTube lives, so it's kind of like a refreshing. Today's Falcon wear day, spirit wear. Okay, maybe, do you guys think that you can see it from phones? Like the commenting part? Okay, so I'm testing things out. Hi, Maya. Okay, so I'm on my phone, but I just don't see the comments. I don't know where to look, Naomi. Oh, comments. It says I could add a public comment, but I don't see the other comments. Oh no, I hear my son crying. Okay. The reason that I'm trying to use either my phone or iPad to do this, for those of you just joining, is that I'm trying to avoid that really like awful delay. Oh, Tom, you can't see the comments either, right? So are you guys on computers right now that you can see the comments? Maybe I have an old computer I could bust out. Let me see. Okay, we still got 3 minutes. Let me see if I can find this. Wait, Emily, you're on your phone and you can see the comments? Oh, okay, because this computer is dead, so it's probably going to take me a while to get it plugged in, but maybe I'll just plug it in just in case. All right, I'm a mess here. Emily, stop. Everything works for you. Okay, wait, so how can Emily see the comments and I can't figure that out? Emily, are you on an iPhone? Like literally when I say comments, oh, you cannot see that at all. Weird. That does not show up very well. Yeah, it says chat publicly under the video. Tom, if you're an 80-year-old, then what does that make me? Chat publicly. Okay, well, I found a computer. It's a very old computer, but maybe it'll work. It is chat, not comments. Oh, hi, Mr. Jens. We're just trying to figure out if I could avoid that delay. But it seems like my iPad and my phone don't show me the comments next to the like and dislike. Like and dislike. Okay, I have like, dislike, and then I see share, save, and report. How come some people can see cooler features than I can? It's 10 o'clock here, so we're going to be getting going in like 1 second. I'm going to see if I can pull it up on my computer. Again, hi everyone. Hi Melody. Hi Anna and Anna. And Caleb and Jasmine. Hi everyone. Makara, Colette. Oh, so many of you today. Wonderful. If you've been on these before, I've had trouble with a really long delay between when you guys write something and when I can see it. But I know that that's not the case for you guys. So hi, Natalie. Hi, Sophia. Hi, Erica. So I'm trying to see if I can view this on another like device so that I can see the comments like live instead of at a delay. But I'm technologically challenged apparently. But it says some of the people. Yeah, Joey, how is everyone? Well, I guess I could try Mr. John's suggestion. I think that I'll just have to deal with the delay today. I haven't been out of my house in years. Tom. Oh, hi, Lauren. Good to see you. Well, see that you're on. Not that I can really see you. And Anna, I agree. Sleeping in is much better. I'm actually sleeping until my son wakes up. So like around like 6:37. And I'm having a hard time going to bed at night because I'm not tired. I'm usually so tired from waking up at 4. All right, let me get this situated here. All right, so we're gonna just start quickly at the beginning with all of our different rules, and we'll see how far we can get in like our 20 minutes or so. Hi, Felicity. Hi, Hannah. Oh, I miss all of you so much. Okay, so our first idea with a circle was just what a tangent is. Okay, so again, a tangent is a point that hits a circle at one spot. We learned that it is perpendicular to any radius that you draw. So it made some right angles. So on the progress check you guys did yesterday, there was a problem about like a satellite being out here and this being the Earth. And then they gave you some different measurements. And keep in mind that this is the radius and this is the radius. So we're going to be able to put that in there twice. And then Pythagorean theorem is what we'll use to solve any sort of length question that involves a radius and tangents. So that was kind of the first idea about tangents. And then, hi, Janvi. And then we started looking at something called a central angle. So a central angle has the vertex of the angle being at the center. That's kind of obvious. Oh, we've got a visitor. Say hi to Chloe. Hi, Chloe. All right. So the central angle is the easiest relationship to learn because it's just equal to the arc. So if our central angle was like 85 degrees, then our arc is also going to be 85 degrees. Okay, so this is called an intercepted arc. So those are going to be the same. And that makes it, oh no, Chloe. Sure. Hi again. Sorry. Oh, she's very pesty. Can you get down? Okay. So those are going to match. Then we moved on to inscribed angles. I think maybe we'll just talk about all angle stuff first. So an inscribed angle, instead of the vertex being on the edge of the circle, or at the center of the circle, I'm sorry, it gets pulled all the way over here to the edge of the circle. Now, as we stretch this angle back and back, the angle gets smaller and smaller. Sorry about geometry live stream can't cover camera. Now the relationship between this intercepted arc, so that's still the arc that's inside of the angle. It turns out that the angle is half of the arc. So this would be 85 divided by 2. That's how many degrees that angle would be. Okay, so those were our first two relationships. Then we saw if the angle is even further back, like if the vertex of the angle is outside of the circle. So now instead of creating it by 2 radii or 2 what we call chords, these are called chords, right? They start on the edge of the circle and they end at the edge of the circle. Okay, this is another chord. Now these, does anyone know what this is called when it's partly outside and then goes all the way through the circle, hitting it twice? I'm gonna allow for the frustrating delay while you guys comment on that for a second. I think I might give us some different numbers. Wonderful, yes. Hi, Madeline, hi, Anna. Yeah, that's called a secant. So when it's part outside and part inside, that's called a secant. So when we have like these 2 secants, now if we follow along this angle, here's one arc that's inside. I've got another color here. Here's one of the arcs that's inside, and then here's yet another arc that's inside. Now, this is something that you guys are going to explore in that GeoGebra activity, but it does have, this angle does have something to do with half, just like this one had something to do with half. But if it's getting even smaller, and we talked about this on, what's today, Wednesday, we talked about it on Monday, that angle ends up being half the difference of these 2 arcs. Okay, now when you go through the GeoGebra activity, and that's something that you're working on, I posted, Mr. Johnson and I posted on Google Classroom, but it doesn't let you in GeoGebra measure an arc, like just measure the arc, like how you can measure an angle. What it does let you do though, is it lets you measure central angles. So let's say that you're on the activity And you have created this diagram. So this is like our secant angle that we've created. And we want to measure how many degrees is this arc. What you're going to have to do is you're going to have to measure this angle right here, that central angle, and that's going to be the same as this arc. So that way you can figure this out, okay? Now, I see a couple questions coming in here. So no matter how far out the angle is, it's the same formula to find it. Yes, so what's nice about these rules is if you just focus on the question, where is my vertex? Okay, so if you think, where is my vertex? If the vertex is at the center of the circle, okay, that's called a central angle. And then this number is the same as the arc. Okay, so the central angle is the same as the arc measure. Now, if the vertex is on the edge of the circle, anywhere on the edge, now the angle, let's say that's 45 degrees, is half of the arc. So maybe that's a 90-degree arc, okay? Now, even if it's at the edge of the circle, here's another example like this one. You might have it on the edge of the circle like this, where one of the lines maybe is secant, or it could stop here at a chord, either way, but one that goes all the way through the circle, and then one that's tangent. Because the vertex is still on the edge of the circle, just like it was here, the vertex is at the edge of the circle, it's going to keep that relationship that the angle is half of the arc, where the arc is double of the angle. So how these problems might work is, let's say that we said that this major arc, now something to know about a major arc is if we had some like names of points here, let's say we said A, B, C. Yeah, okay. So if I wanted to tell you that this big arc was, let's say, 260 degrees, something like that, how they would write it is they'd say arc ABC. So that's telling us to go from A through B on the way to C. If they just said arc AC, then they're telling you to go the shortest possible path. Okay, so the shortest way from A to C, that's going to be the minor arc. But if they want you to go the long way around the circle, they're going to give you 3 letters, or they might put the word major. They might say on major arc AC, and major means more than halfway across the circle, so like the long way. So if this were to be 260 degrees for this major arc, then that would leave us with 100 degrees for the minor arc AC. So then if we were asked to find this angle right here, because that angle is on the edge of the circle, hey Caleb, hey Molly, since that angle is on the edge of the circle, it's going to keep that same relationship. I know this diagram looks a little bit different than this one, but keep asking yourself, where is my vertex? If it's at the center, then the angle and the arc match. If it's on the edge of the circle, then the angle is half of the arc. So again, it would be half of the arc, making this angle right here 50 degrees. All right, how are we feeling with that so far? Oh, hi, Kate. Good to see you on here. Hi, JD. I don't know if I really know you, but I know that your name is JD. Okay, so our next case is, oops, dropped my phone. Our next case is when the vertex is outside of the circle. So the vertex could be outside of the circle in a few different cases. Let me try to draw that a little bit better. Our vertex could be outside of the circle for our angle, and it looks like a sideways ice cream cone. This would be our tangent case, where it could be outside of the circle with a secant case. Okay, two secants, but this angle right here outside of the circle. There's even another case where one is tangent and one is secant. Okay, in all of these situations, the vertex is outside of the circle. So when it's at the center, they match. When the vertex is on the edge, it's just half of the arc that it matches to. We call it the intercepted arc. And then when it's outside in any of these cases, okay, angle Y, angle X, and angle W, they all have the same relationship. In every case, there's two intercepted arcs. So this angle has first this intercepted arc, okay, connecting those 2 points on the shorter route, and then the longer route. So those are the two arcs. Here in the secant case, these would be our two arcs that are intercepted. And then here, we'll follow that along. Here's our first intercepted arc. And then here is our second intercepted arc. So they're always going to have two arcs to consider now. In those cases, there's only one arc to look at. And it matched, or it was half of the arc. But when we have two, there's a little bit more that we have to do with them, okay? So again, there's two arcs. This is one of them, and this is our other one. It can be consistent with that. So we've got our outer arc and our inner arc. Outer arc, inner arc, outer arc, inner arc. So what you're going to be finding as you're doing your activity, and we've already kind of talked about this, some of you are working ahead and some of you aren't, so it's a little bit confusing. Maybe you've already done section 12.4 on the online textbook and you already know all this. But what ends up happening is you're going to take your bigger arc, you're going to subtract your smaller arc and divide by 2. So our angle, when your vertex is outside, okay, so if your vertex is outside, our angle is 1/2 the big arc minus the small arc. Okay, so we've got that rule. So whatever number this is, you're going to subtract the smaller arc, this one, so you have the difference of the arcs, and then divide that by 2 to get out here. These angles, the further we pull them out, the smaller and smaller they are. So subtracting is kind of how we can get them to be smaller, okay? Hey, Shane. So no matter what the case is, we can make up some numbers, like let's say that this is 100 degrees here. Use black so you can see a little bit better. 100 degrees here, and that one is, let's say, 70. So what we'll do is we'll subtract those two arcs, big arc minus small arc, otherwise you'll get a negative. So the difference of our arcs is 30. Take half of that, that's going to give us angle W to be 15 there. Okay, and that rule applies in all of these different situations. Now there's one last case. Where could my vertex be? We looked at outside. We looked at when it was on the edge of the circle. We looked at when it was at the center of the circle. So we looked at the center. That's when these match. We looked at when it was not at the center, but at the edge of the circle. Now that angle is half of this arc. We looked at when it was outside. This angle is half the difference of the arcs, okay? And then there's one final case, and we're not going to go over that quite yet because I want you to try to be able to discover it on the activity as you're working on that tomorrow or the next day. But the last possible case is, what if our angle has a vertex not at the center of the circle, not at the edge of the circle or outside? What if it's just some random point inside of the circle? So this angle actually has two intercepted arcs, because this angle, if you look at its vertical angle pair right here, those angles are the same by vertical angle theorem. So this angle intercepts this really tiny arc right here, but that same angle intercepts this big arc on the other side. The same angle goes to two different numbers and it's in between them. So maybe you could start thinking about what relationship might they have. So far, except for the central one, everything had something to do with 1/2. So we looked at 1/2 of the arc when there was only one. We looked at 1/2 the difference of the arc when it was pulled outside. And when it's inside, it is going to have something to do with 1/2, but you're going to have to figure out what should we do with those two numbers, those two measures of the arcs. Okay, that's kind of what you're going to be exploring in the activity. Again, some of you might have already seen this if you've been working on 12-4, but there's going to be one final case. Does anyone have any guesses on it? I'll give you a second to look at that. This delay is brutal. Maybe I'll try to hijack my husband's computer for next week. Yeah, so JD, it is related to 1/2, but we had like two arcs. So let's say this is the angle that we're trying to find, and this is like 120 degrees, and this is maybe 40 degrees. So that same angle relates to two different numbers. The smaller quarter circle arc. I have, Mr. Johns, I have to think that someone knows this. Great idea. Now, Hannah, the idea that, or the relationship that you brought up, the 1/2, the difference, that's going to be when it's outside. So when our vertex is outside of the circle, that's where we're going to subtract these two arcs and take 1/2. If you look at Mr. John's little joke, instead of taking half the difference of the two numbers to get our arc, to get our angle, we're looking more at half of someone knows it. I'm sure you've already typed it, but there's just a delay. So this is going to come out to be 80 degrees. Okay, and you'll discover that more. Maybe you can think, yeah, good job, JD. 1/2 the sum. Now, I don't want to hold you here much longer, but those are angle relationships, okay? So everything we talked about today are all the different relationships with angles in a circle. You're seeing that there's, good, you guys are doing great on that. There's so much to learn, so many different theorems about circles. So we were looking at today the 4 different cases of where could our vertex be within a circle, and what does the angle what does the angle become? So when it's at the center, they're the same. When it's on the edge of the circle, it's half. When it's outside of the circle, it could look like that or it could look like this. In both cases, we do 1/2 the difference of the two arcs. Subtract the arcs and take 1/2. And then finally, our last case, if it's not at the center, just somewhere inside, it's the average, basically, is what you're doing. If you take half the sum of them, you're averaging the two arcs because it's inside. So tomorrow, Mr. Johns is going to be focusing, well, we didn't really talk about this, but I'm kind of assigning him. Mr. Johns is going to look at more of the relationships with the segments. Now, one of the segment things that you already learned was in two tangents, like the sides of the ice cream cone, these two lengths are the same. But we need to talk about these lengths and how do these lengths all relate. Unrelated to angles, there's relationships about the lengths, okay? So we're going to talk about segments tomorrow with Mr. Johns, and this is your review on angles. So thank you all for tuning in. If you haven't already commented on here, especially if you're one of my students, just comment saying hi or something so that I see that you're in here. I'd love to know who showed up today, all right? And thanks again. All right, you guys have a good rest of your day. Today is Falconware Day. So if you're on Instagram, you can tag Wheat North, or I think it's WNHS Falcons, and you can get in the little Spirit Week thing, all right? All right, bye. Hi, Kaylee. Hi, everyone. See you later. So many people saying bye. I guess I'll just leave it for just a second in case I missed anyone. No, I think you are all in there already. Bye-bye.